welcome to this problem walkthrough. Today, we'll explore the problem titled Maximum Number of Achievable Transfer Requests. This fascinating challenge involves optimizing the number of transfer requests that can be fulfilled while maintaining balance constraints. Let's dive in and uncover the optimal approach together. In this problem, we are working with a group of buildings, numbered from 0 to n1. Each of these buildings is either sending or receiving transfer requests. These requests are provided in the form of a 2D array called requests, where each entry is represented as a pair, from _i to _i. Here, from _i indicates the building initiating the transfer, and to _i specifies the building receiving it. Now, our goal is to determine the maximum number of requests we can approve while maintaining balance. Balance means that for every building, the total number of incoming requests must equal the total number of outgoing requests. To summarize, we need to select the largest possible subset of requests that satisfies this condition. The problem also specifies the constraints. The number of buildings n can range from 1 to 20, and the number of requests m can go up to 16, making it computationally feasible to explore possible combinations. Let's look at an example to better understand the problem. Suppose we have 5 buildings in the following requests: 0, 1, 1, 0, 1, 2, 2, 3, 3, 4, 4, 0. Here, the output is 5, meaning we can approve all 5 requests while maintaining the balance condition. Let's break this down. Building 0 sends a request to Building 1 but also receives one from Building 4, so its net change is 0. Similarly, Building 1 sends a request to Building 2 and receives one from Building 0, again a net change of 0. The same logic applies to the other buildings. Each building sends and receives exactly one request, ensuring there is no imbalance. Since all requests can be approved without violating the balance condition, the output is the total number of requests, which is 5. In this example, all buildings satisfy the balance condition, meaning the incoming requests match the outgoing requests for each building. This allows us to approve all the transfer requests. Now, let's consider another example. Here, we have 3 buildings in the following requests: 0, 0, 1, 2, 2, 1. The output is 3, indicating that all 3 requests can be approved. Let's analyze why. Building 0 sends a request to itself, which doesn't affect its balance. Building 1 sends a request to Building 2 and receives one from Building 2, so its net change is 0. Similarly, Building 2 sends one request to Building 1 and receives one from Building 1, maintaining its balance as well. Since the balance condition is met for all buildings, all requests are valid, and the output is 3. Again, in this example, all buildings maintain balance, allowing us to approve every request. Let's move on to another case. Here, we have 4 buildings in the following requests: 0, 3, 3, 1, 1, 2, 2, 0. The output is 4, meaning all 4 requests can be approved. Let's see how this works. Building 0 sends a request to Building 3 and receives one from Building 2, so its net change is 0. Building 1 sends one request to Building 2 and receives one from Building 3, maintaining balance. Similarly, Building 2 sends a request to Building 0 and receives one from Building 1, while Building 3 sends one request to Building 1 and receives one from Building 0. Since the balance condition is satisfied for all buildings, all 4 requests can be approved, leading to the output of 4. As we can see, this example also satisfies the balance condition for all buildings, so every request is valid and can be approved. Now, let's wrap up by discussing the constraints and edge cases. The constraints specify that there can be up to 20 buildings and at most 16 transfer requests in the input. This ensures the problem is computationally manageable. Some important edge cases to consider include scenarios where there are no requests at all, in which case the output is 0 since no transfers can be approved. For a single building, the output would be the number of self-loops, such as 0, 0 requests. Additionally, if the requests are inherently imbalanced, meaning it's impossible to satisfy the balance condition for all buildings, the output will be less than the total number of requests. Finally, in cases where all requests already satisfy the balance condition, the output would simply be the length of the requests array. To solve the maximum number of achievable transfer requests problem, we are tasked with maximizing the number of requests that can be fulfilled while ensuring that the net balance of transfers across all buildings is zero. This is a combinatorial optimization problem, and one approach we can consider is a brute force method using exhaustive search. The idea is straightforward: we generate all possible subsets of requests and validate each one to check if it satisfies the zero net balance condition. Specifically, for each subset, we calculate the net transfer change for every building. If the net balance for all buildings is zero, we know the subset is valid, and we update the count of valid subsets. However, the computational complexity of this approach is significant. Generating all subsets requires O(2 to the power of m) time, and validating each subset involves O(n*(m), resulting in a total complexity of O(m*(2 to the power of m). This makes the brute force approach impractical for large inputs, but it is a useful baseline for understanding the problem structure. The brute force approach has some advantages and disadvantages. On the positive side, it is easy to implement and guarantees correctness by exhaustively checking all possible subsets of requests. However, the major drawback is its exponential time complexity, which makes it infeasible for larger inputs, particularly when the number of requests exceeds 20. To address this limitation, we can turn to an optimized approach using backtracking. The intuition behind backtracking is to avoid evaluating all subsets blindly. Instead, we explore the requests recursively, deciding at each step whether to include or exclude the current request. By maintaining the current balance state of all buildings as we explore, we can prune invalid subsets early, which reduces unnecessary computations. If we reach the end of the recursion, we check whether the balance array for all buildings is zero and, if valid, track the maximum number of requests satisfied. This approach introduces a level of efficiency by focusing only on potentially valid subsets. When analyzing the backtracking approach, we find that its worst-case complexity is still O(2 to the power of m), as it may need to explore all possible subsets. However, pruning allows us to skip over invalid subsets, which can reduce the effective number of subsets we need to evaluate, depending on the problem's constraints. In practice, this makes backtracking slightly faster than brute force in many cases. Additionally, the approach is more intuitive for small inputs and constraints, as it dynamically narrows down the possibilities. That said, backtracking still struggles with scaling. For larger values of m, the exponential nature of the problem remains a bottleneck, and the performance gains may not be sufficient. To further optimize the solution, we can turn to a bit masking approach combined with pre-computation. This method focuses on reducing redundant calculations, making it more efficient for smaller constraints. The bit masking with pre-computation approach introduces a way to efficiently handle the validation of subsets. Using bit masks, we represent each subset of requests and pre-compute the net balance for each subset. This avoids recalculating balances repeatedly during the validation step. The process involves three main steps. First, we generate all subsets of requests using bit masks. Second, we pre-compute the net balance for each subset in O(m*(2 to the power of m) time. And third, we iterate over the subsets to check if the pre-computed balance is zero, tracking the subset with the maximum number of valid requests. While the total complexity remains O(m*(2 to the power of m), this method avoids redundant computations, making validation faster and the implementation more streamlined. However, it comes with its own trade-offs. The increase in memory usage due to pre-computed balances can be significant, and the approach is still impractical for larger values of m, such as when m exceeds 20. After evaluating the different approaches, the brute force method was dismissed due to its inefficiency and lack of scalability. While both backtracking and bit masking with pre-computation offer optimizations, the latter was chosen as the final strategy because it avoids redundant calculations and simplifies subset validation. Backtracking can dynamically prune invalid subsets, but it still involves some repetitive calculations. On the other hand, bit masking uses additional memory to pre-compute balances, but this trade-off results in faster validation and easier implementation for smaller constraints, such as when the number of requests is 20 or fewer. A key realization, or aha moment, was the understanding that pre-computing balances significantly reduces redundant work, even though it doesn't change the overall exponential complexity. The final complexity for the chosen strategy is O(m*(2 to the power of m), and while it doesn't scale well for larger inputs, it strikes a balance between simplicity and efficiency for smaller problem sizes. In this problem, we need to determine the maximum number of transfer requests that can be fulfilled while ensuring that the net population change in every building is 0. Each request is represented as a pair, from, to, signifying a transfer of one person from the from building to the to building. For example, if there are 3 buildings and the requests are 0, 1, 1, 2, 2, 0, 1, 0, we can fulfill up to 3 requests while still maintaining a balance across all buildings. To solve this, we'll use an exhaustive search approach. The idea is to try all possible subsets of requests and find the largest subset that satisfies the balance condition. To accomplish this, we generate all subsets of the requests, verify which ones maintain the balance, and track the largest valid subset. Let's break down the steps in detail, starting with how to iterate over all subsets of the requests list. The first step is to generate all possible subsets of the requests list. If there are m requests, there are 2 m subsets to consider. For each subset, we'll evaluate whether it satisfies the net balance condition. To do this, we use a balance array of size n, where each index represents a building. Initially, all values in the balance array are set to 0. As we process a subset, we update the balance array for each request, from, to, by decrementing balance, from, by 1 to represent a person leaving and incrementing balance, to, by 1 to represent a person arriving. After processing all requests in a subset, we check whether the balance array is 0 for all buildings. If it is, the subset is valid, and we calculate its size. If this size is larger than the current maximum, we update the maximum. Additionally, we can optimize this process by terminating early if we detect that the balance array contains a non-zero value during validation, as this immediately invalidates the subset. Once all subsets have been evaluated, we return the size of the largest valid subset. This exhaustive search approach involves evaluating all subsets of the requests list, making the time complexity exponential. Specifically, the complexity is 2 to the power of m asterisk n, where m is the number of requests and n is the number of buildings. The 2 m factor arises from generating all subsets, and the n factor comes from validating the balance array for each subset. To improve efficiency, we can prioritize subsets in decreasing order of size. When a valid subset is found, we can terminate early since no larger subset will be valid. The key condition to check for validity is ensuring a 0 net balance for all buildings, making the validation step straightforward. Edge cases to consider include scenarios where the requests list is empty, in which case the result is 0, and situations where n equals 1, where all requests are automatically valid since they involve only one building. These insights help refine the algorithm and reduce unnecessary computations. The balance array plays a crucial role in this approach. It tracks the net population change for each building during subset validation. For example, if there are 3 buildings and the subset of requests is 0, 1, 1, 2, the balance array evolves as follows. After processing 0, 1, the array becomes -1, 1, 0, indicating one person left building 0 and one person entered building 1. After processing 1, 2, the array becomes -1, 0, 1, showing that one person left building 1 and entered building 2. Another essential component is the subset generator, which systematically generates all possible subsets of the requests list. For a list of requests like 0, 1, 1, 2, the subsets would be the empty set, the subsets with one request, 0, 1, and 1, 2, and the full set, 0, 1, 1, 2. These tools are integral to evaluating all potential solutions and identifying the largest valid subset. The pseudocode for this algorithm begins by iterating through all possible subset sizes using the combinations function. For each subset, we initialize the balance array and update it based on the requests in the subset. After processing a subset, we check if all buildings are balanced using Python's all function to quickly verify if every value in the balance array is 0. If the subset is valid, we update the maximum count if its size is greater than the current maximum. After evaluating all subsets, we return the largest valid subset size. To optimize further, we can prioritize processing larger subsets first and terminate early when a valid subset is found. Additionally, instead of creating a new balance array for each subset, we can reuse a single array by resetting it after each subset's validation. These optimizations reduce redundant computations and improve memory efficiency, making the algorithm more practical despite its exponential complexity. This Python implementation solves LeetCode problem number 1601, maximum number of achievable transfer requests. The task involves determining the maximum number of requests that can be fulfilled while ensuring that the net population change for every building is 0. The method maximum requests takes two inputs, n, the number of buildings, and requests, a list of transfer requests. Each request is represented as a pair, from, to, indicating the movement of one person from one building to another. The solution employs a brute force approach by iterating over all possible subsets of the requests. This is done using bit masking, where each bit of an integer represents whether a specific request is included in the subset. The total number of subsets is 2*total_requests, which ensures all combinations are covered. A helper function is _valid checks if a given balance array satisfies the condition that all elements are 0, indicating no net change in population across all buildings. For each subset of requests, the algorithm calculates the balance array by decrementing the population for the from_building and incrementing for the to_building. If the resulting balance is valid, the count of requests in the subset is compared with the current maximum and updated if necessary. The algorithm has a time complexity of 2 to the power of m*n, where m is the number of requests and n is the number of buildings. While this approach is not optimal for large inputs, it is sufficient for the problem constraints and ensures correctness by exhaustively exploring all possibilities. Here, we start with the Java implementation of the solution. The maximum requests method begins by initializing two variables, max requests, which will store the maximum number of achievable requests, and total requests, which holds the total number of transfer requests provided in the input. The main logic involves iterating over all possible subsets of requests using a bitmask approach. For each bitmask, we initialize an array called balance to track the net inflow and outflow of requests for each building. We also use a variable, count, to keep track of how many requests are included in the current subset. The inner loop processes each request in the subset. If the bit corresponding to a specific request is set in the bitmask, we extract the from building and to building from the request, decrement the balance for the source building, increment the balance for the destination building, and increase the count of active requests. After processing all requests in the subset, we check if the current subset is valid by ensuring that the balance array reflects 0 net changes for all buildings. If the current subset satisfies the validity condition, we update max requests to store the maximum of its current value and the count of requests in the valid subset. Finally, after all subsets have been evaluated, the method returns the max request's value. To determine validity, we use the helper method isValid, which iterates through the balance array. If any value in the array is not 0, it returns false, indicating that the subset creates an imbalance across buildings. Otherwise, it returns true. This helper function ensures that only those subsets where all buildings maintain a net balance of 0 are considered valid, which is critical for achieving the problem's constraints. The combination of bit masking and the balance checking logic makes this an efficient way to explore all possible subsets and find the maximum number of achievable transfer requests. Here, we begin with a basic example that involves 2 buildings and 2 transfer requests. The input specifies that there are 2 buildings, and the requests indicate a transfer from building 0 to building 1, and another from building 1 to building 0. First, we initialize max_requests to 0, which keeps track of the maximum number of achievable requests. The total number of requests is 2, so we will iterate over all possible subsets of these requests, represented by a bitmask. Since there are 2 requests, there are 2 squared, or 4 subsets in total. For subset 0, where no requests are included, the balance array remains 0, 0, meaning no net change in the number of people in each building. Because all values in the balance array are 0, this subset is valid. However, no requests are included, so max_request stays at 0. Next, we evaluate subset 1, represented by the mask 0, 1. Here, we include the first request, which transfers one person from building 0 to building 1. As a result, the balance array becomes -1, 1, indicating that building 0 loses one person while building 1 gains 1. Since the balance array is not entirely zeros, this subset is not valid, and max_requests remains unchanged. For subset 2, represented by the mask 10, we include only the second request, which transfers one person from building 1 to building 0. The balance array becomes 1 minus 1, representing the inverse of the previous case. Again, the balance array is not valid, so max_requests is still 0. Finally, in subset 3, represented by the mask 11, we include both requests. The balance array becomes 0, 0, because the changes cancel each other out. This subset is valid, and since it includes two requests, we update max_requests to 2. At the end of this example, the maximum number of achievable transfer requests is 2. Moving to a more complex scenario, we now consider an example with 3 buildings and 3 requests. The input specifies transfers from building 0 to 1, from building 1 to 2, and from building 2 back to 0. Once again, we initialize max_requests to 0, and the total number of requests is 3. This means we will evaluate all 2 cubed, or 8, subsets of these requests. By exhaustively checking each subset, we aim to find the maximum number of valid requests that can be achieved while maintaining a 0 balance for all buildings. For subset 0, where no requests are included, the balance array remains 0, 0, 0, indicating no net changes across the 3 buildings. Since all values in the balance array are 0, this subset is valid, but it includes no requests, so max_requests remains at 0. Now consider subset 7, represented by the mask 111, which includes all 3 requests. The balance array becomes 0, 0, 0, because the transfers from building 0 to 1, from 1 to 2, and from 2 back to 0 perfectly cancel out. This subset is valid, and since it includes all 3 requests, we update max_requests to 3, which is the maximum possible for this example. Therefore, the final output for this case is 3. In this example, we introduce a case where not all requests can be achieved simultaneously. The input specifies 3 buildings and 3 requests, one from building 0 to 1, one from building 1 to 2, and one from building 1 back to 0. As before, we initialize max_requests to 0 and evaluate all 2 cubed, or 8, subsets of requests. For subset 3, represented by the mask 011, we include the first 2 requests, a transfer from building 0 to 1 and another from building 1 to 2. This leads to a balance array of -1, 0, 1, which is not valid because some values are not 0. As such, this subset does not contribute to the maximum number of achievable requests, and max_requests remains unchanged. Now, consider subset 5, represented by the mask 101. This subset includes the first and third requests, a transfer from building 0 to 1 and another from building 1 back to 0. The balance array becomes 0, 0, 0, because these 2 requests cancel each other out, leaving no net change in any building. Since this subset is valid and includes 2 requests, we update max_requests to 2. At the end of this example, the maximum number of achievable transfer requests is 2, as no larger valid subsets exist that maintain a 0 balance for all buildings. Here, we analyze the time complexity of our solution step by step. First, we consider the outer loop, which iterates over all subsets of the requests array. Given that the number of requests is total_requests, the total number of subsets is 2_total_requests. Thus, the outer loop runs in O, 2_total_requests. Next, for each subset, the inner loop determines which requests are included based on the bitmask representation. This involves iterating through all total_requests and, for each request, updating the balance array and counting the requests. Therefore, this inner loop runs in O, total_requests. Finally, after processing a subset, the is_valid function validates whether the balance array has all elements equal to 0. Since the balance array has size n, this validation step runs in O, n. Combining these steps, the time complexity for processing one subset becomes O, total_requests plus n. Multiplying this by the number of subsets, 2_total_requests, gives us a total time complexity of O, 2_total_requests asterisk, total_requests plus n. Assuming total_requests is much larger than n, this simplifies to O, 2_total_requests asterisk total_requests. Now, let's discuss the space complexity of the solution. The primary space usage comes from the balance array, which is of size n, leading to a space requirement of O, n. Additionally, there are a few other variables, such as max_requests, count, and the bit mask, which only require constant space, or O(1). Combining these, the overall space complexity of the solution is O(n). To provide some context, we can compare this solution to a naive brute force approach. A brute force method would involve generating all permutations of the requests array to check every possible order of execution, resulting in a factorial time complexity of O total_requests. In contrast, our solution significantly improves on this by considering only subsets of requests, reducing the time complexity to O total_requests total_requests. However, it's important to note that the solution is still exponential in time complexity, which is unavoidable for this problem due to the need to evaluate all subsets of requests. Let's now examine the best, average, and worst-case scenarios for this algorithm. In the best case, all requests in the first subset checked are valid and perfectly balance the buildings. While this scenario is theoretically possible, it is extremely rare and doesn't reduce the overall exponential complexity of the problem. For both the average and worst-case scenarios, the algorithm must iterate over all total_request subsets and validate each one, resulting in the same time complexity of O total_requests total_requests. To justify this big O notation, we recognize that the exponential time complexity stems from evaluating all subsets of the requests array, which is a combinatorial necessity for this problem. Each subset requires O total_requests operations to update the balance array and O(n) operations for validation, resulting in the overall complexity of O total_requests total_requests. On the other hand, the space complexity remains linear at O(n), as it is dominated by the size of the balance array. When tackling this problem, there are several common pitfalls to watch out for. First, failing to check all combinations can be a major issue. Many people try to use greedy algorithms, such as prioritizing the largest requests, assuming this will yield the optimal solution. However, this problem requires evaluating all possible subsets, as skipping subsets can lead to suboptimal answers. Next, it's critical to remember the zero balance constraint. Some solutions focus solely on maximizing the number of fulfilled requests and overlook the requirement that each building's net balance must equal 0. Ignoring this constraint violates the problem's rules and results in incorrect answers. Another mistake is inefficient pruning when using backtracking. Without early stopping conditions, like skipping subsets that already violate the zero balance rule, you can end up performing unnecessary computations, which can significantly slow down your solution. Lastly, mishandling the state array during recursive backtracking is a frequent issue. If you fail to properly undo changes to the balance array when backtracking, you risk corrupting the state, which can lead to incorrect results and hard-to-diagnose bugs. Overcomplicating the solution is another common mistake. Sometimes, people misinterpret the problem and introduce unnecessary complexity, such as attempting to detect cycles or applying advanced graph algorithms. However, the problem can be solved with simpler methods, like backtracking. Now, let's discuss important insights for interviews. The key insight here is that this is a subset selection problem with constraints. The challenge lies in maximizing the size of the subset while satisfying the zero balance condition. Recognizing patterns is also crucial. For example, problems involving subset evaluation often call for backtracking, as brute force approaches become infeasible for larger inputs. To optimize your solution, leverage pruning techniques during backtracking. For instance, track the current balance array and terminate exploration of subsets that lead to invalid states. Additionally, when explaining your solution in an interview, make sure to clearly communicate the trade-offs. Highlight how pruning reduces the search space and why it's a more efficient choice compared to brute force approaches. Understanding related problems can deepen your grasp of the techniques required here. For instance, LeetCode 78, subsets, is a foundational problem that teaches the basics of generating subsets. This is a great starting point to build your understanding of subset exploration. LeetCode 473, matchsticks to square, introduces similar constraints and uses backtracking with state management, making it highly relevant to this problem. Another valuable problem is LeetCode 51, nqueens, which is also a constraint satisfaction problem that relies on backtracking. Finally, LeetCode 980, Unique Paths 3, involves exploring valid configurations through backtracking, providing additional practice in balancing constraints within a search space. These problems not only help you refine your skills but also allow you to recognize patterns and strategies that can be applied to a wide range of questions. There are also alternative approaches to solving this problem, each with its own trade-offs. A brute force approach involves evaluating all 2 to the power of n subsets of requests to find the largest valid subset. This method is straightforward to understand and implement, but it is computationally expensive, with a time complexity of 2 to the power of n*n, where n is the number of requests. A more efficient option is backtracking with pruning. In this approach, you recursively explore subsets while maintaining a balance array, and prune invalid states early to save computation time. While this is faster than brute force, it requires careful implementation to avoid errors, particularly in managing the state. Another approach is bit masking, where subsets are represented as bit masks, and you iterate through all configurations, checking the validity of each mask. This method is space efficient and can be elegant, but it can also be challenging for beginners to implement. Like brute force, its time complexity is 2 to the power of n*n, but it offers a different perspective on subset exploration. Choosing the right approach depends on the specific context and your familiarity with the techniques. Great job! We've reached the end of this problem breakdown. To summarize, we explored an optimized approach using backtracking to maximize transfer requests while maintaining balance constraints. Key takeaways include understanding constraint satisfaction and the power of backtracking. Thanks for watching. Don't forget to like, share, and subscribe. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!